Are you guys ready up there? Okay, so hopefully you had some time to play with that a little bit. You might have scrolled down and been tempted to do this load solutions thing. We put this in here because we want these notebooks to be useful for folks who are not here live with us. But resist the temptation when we're doing these exercises to just load the solutions and look at them. The value here is really thinking about this and exploring it on your own. But the solution, I can just show you the way that I did this. I used faces equals fetch elevated faces. And remember, this is a function, so you need this open close parenthesis at the end there to actually get the data. And I drew a figure just like above. I adjusted the subplots just like above, and then looped through the first 64 images, added a subplot, and then showed the ith face. And let me just show you, if you take away if you use the default color map, what did I do wrong now? Pilot, oh, not defined, oh yeah. I import it there, yep. So I didn't run the cell above, and that's what killed me right there. So if I do this with the default color map, you get something really weird and interesting. Yes?
I asked you to repeat any questions anyone asked.
Okay.
I'm not getting questions.
Okay. He was asking that if I could repeat questions that are asked to me. Yes. Sorry. So if you use cmap equals plt.cm.bone instead, this is just one that looks a little better for these images, and you actually get kind of black and white images. So this is the faces data set, and again, just like before, we were seeing that the digits are zoomed in right around, and everything's sort of regularized. This is the same thing with the faces. To plug these data sets into the machine learning algorithms, you need to have regularized data. You need each feature to be referencing the same thing. And in the case of facial recognition, it's an interesting question how you actually find the faces within images. And there are actually going to be some talks later on this week that delve into that question a little bit. And we're not going to go into that here, but it's, like I said, it's an interesting piece of the puzzle. So does that make sense to everyone working with these data sets? Yeah? Yeah, he was asking, he said he had to reshape his images before they were displayed in ImShow. I think probably what you did is you used data here instead of images. Is that right? No?
Yes.
Yeah. So the data is the number of samples by the number of features. These images are kind of pre-reshaped for you, so you can just plug them straight in. Anything else right now? Great. So just want to double check how our schedule is looking. Yeah, okay. So we'll pull up this 2.2 notebook now, the feature extraction. So this is getting a little bit into the questions that people have asked about how do you take your own data and put them into a format that Scikit-Learn can read. How do you decide what these features are in your feature matrix? And we'll talk a little bit about how to do that for real world data. So first, there are a number of different types of features that you might have in a data set. You might have numerical features like we've seen before. Here we'll load the iris data again. And if we print the iris.data, this is kind of a repeat of some of the stuff we saw before. But we see that the iris data is, they're real valued features. They're measurements in centimeters. They're continuous features. If we scroll down a little bit, we can see that you might imagine also having categorical features. So imagine if this biologist out in the field said, I have measured the color of the iris too, and said it's either red or it's blue or it's purple, right? So how would you deal with categorical features like that? You might imagine doing something like saying red is 0, blue is 1, purple is 2, and just assigning a number to that. But the problem is with that strategy that most learning algorithms assume that any particular feature is kind of a continuous scale. So if you say red is 0, blue is 1, then the algorithm would assume that 0.5 would be somewhere between red and blue, and 1.5 would be somewhere between blue and purple, that kind of thing. So that's not always the best strategy when you have these continuous features. All right, so when you have discrete features like that. So one of the ways you can do that is to actually create a binary features for each of these labeled things. So for example, you might add to your 4 iris features another one that's 1 or 0, telling you whether the color is purple. A 6th one saying that's 1 or 0, telling you whether the color is blue, and the same for if the color is red. And because this is kind of a common thing to do in machine learning, we actually have these vectorizer objects that do this for you. So imagine you had some data where people were measuring what city something was happening in. So the city was Dubai, London, or San Francisco. And the temperature in each of those cities is given here, I assume in Celsius, because Olivier wrote it. Yeah. We'll forgive him for his Europeanness. Oh, that's true. It's an international standard, so it's my bad, right? Yeah. This is SciPy, and it's not SciPy. It's not PyCon, so we can go with international standards. So yeah, if you tried to assign 0 equals Dubai, 1 equals London, then what is 0.5? It's somewhere between Dubai and London. That doesn't really make sense. So this is where using categorical features is useful. And this dict vectorizer from the feature extraction module is something that does that for you. If we instantiate the dict vectorizer, and then what we're going to do is fit and transform these measurements and get the array out. What did I do wrong? I didn't define these measurements. You always got to run yourselves. Learn from me. If we fit transform the measurements and go to array, and let's print the feature names as well, what we see is in the first feature here is the city equals Dubai, and it's 1 for the first sample and 0 for the rest. Similar for London and for San Francisco. So we have these binary features that tell you what city we're in. And it turns out learning algorithms work a lot better with these binary features than they would if you tried to use a continuous feature representing the city. So this, you might guess that this sort of thing is very useful in text classification. If you're looking at the word occurrence in documents, that sort of thing. These vectorizers are pretty useful for that. Another thing we might use often is derived features, and this goes back to the image processing thing. If you have an image that has a face somewhere in it, but you don't know where that face is, you need to design some algorithm to derive interesting features. So the derived features might be some sort of wavelet transform or some sort of specifically designed filter that kind of looks at your whole image and pulls out something that you think might be interesting based on your intuition or based on what you know you're looking for. And we don't have an example of that right here because it's a pretty complex problem and it depends on the particular situation you're looking at. But you can look at Scikit-Image. It's an interesting package that has a lot of feature extractors designed specifically for image data. I see a question right there.
So the vectorizer is great if you have 3 cities. If you're using the English language, you get this stuff that was sparse.
Yeah, so he was asking, he said the vectorizer is great for 3 features, but if you're using the English language with 10,000 words or something, it's a huge array. And you can actually do that. You can actually output it to a sparse array. I think, is it just sparse equals true? I'm going to do something here. I'm going to press tab. In the constructor, yeah. So when you do dict vectorizer right there, see there's this argument sparse equals true. So let's try that. So if we create the dict vectorizer with sparse output, and then we transform our, what were what were we transforming before? Measurements. Transform our measurements. You see that you get a 3x4 sparse matrix. If we do 2-array, yeah, so this one outputs a sparse with a, so yeah, that works for large data sets. See another question back there.
It's the same thing. You're using 3 floats to encode 2 bits of information at that point, so it seems very efficient.
Right.
Obviously going sparse helps, but even then you're using.
Yeah, the question was about.
Data type to represent what's actually not a very.
Yeah, the question was about storage efficiency. You know, even like he said, even with the sparse representation, you're still using several bits to encode just 2 bits of information. But that's essentially that's what the algorithms need. And as we'll see with Olivier's examples later on in the day, this actually works pretty well, and you can you can classify large text documents with this sort of strategy. So, another question.
Does it matter that the possible ranges for the different elements of the feature vector are different? So here, the first 3 go from 0 to 1, the last one goes from 0.
Yeah. So Brian's question was, does it matter that the ranges for these different values are different? So, for example, here we have 3 that go from 0 to 1. We have 1 that ranges from 18 to 33, and maybe more. And the answer is most definitely yes. It depends on the particular algorithm you're using. But for this reason, we have a lot of feature transformers built into Scikit-Learn that will do some sort of data normalization or data whitening or pre-processing. So if we do, like, for example, from Scikit-Learn .preprocessing import min-max scalar, and let's instantiate that, and then we can actually do scalar.fit transform. Let's see, we need our data, don't we? Let's call this data right here, just so we have it. And if we fit transform our data, then an error occurs. A sparse matrices pass. Yeah, so let's, in this case, let's not use the sparse one just for sake of example. And then we see that it's scaled the values to the same minimum maximum range. So this allows you to, this is one method of pre-processing your data to make it work better with certain algorithms. What's that? Yeah. If you're concerned with the fact that this min-max scalar doesn't support sparse, we encourage you to submit a pull request. We're waiting for that to come out. Yeah.
So all these features are descriptions of the class that you're looking at, yeah?
So the question was what the features are describing. The features are describing measurements of each object. So think back to the iris. For each iris, we measured the length of the petal, length of the sepal, width of the sepal. Here in this example, we're measuring the city name and we're measuring the temperature. And the class label is distinct from those features.
But they describe the class, yeah?
But yeah, the features. The features describe the samples, and then the classes are an overarching label on the features. Does that make sense? Maybe as we do more examples, I think maybe that'll make a bit more sense.
So one obvious disadvantage of splitting up these cities like this is that you might classify a city as being both Dubai and London.
Yeah, the question was if you might end up classifying a city as being both Dubai and London. And this is, again, the difference between features and labels. The features are something you measure. So let's say in this case, the label that you're learning is not what the city name is necessarily. The label might be some overarching thing like whether people think this is a desirable city to live in. So you give the city name and you give the temperature, and you're trying to learn based on, well, city name might not help in that case, but you're trying to learn based on the temperature, say, whether the citizens think it's a desirable city. So again, as we go on and do more examples, I think the distinction between features and labels will make a little bit more sense. But yeah, for now, so I should comment on one more thing. Text feature extraction, that's a whole nother area of the field, and we're going to get to that later in the advanced tutorial this afternoon. Olivier is going to talk this morning. Oh, we're going to talk about that this morning. Awesome. So, so that concludes the section on data. I think just for the sake of time, we're going to move along here. I think we've had time to ask a number of questions. And Olivier is up next, I believe. Is that right? Already? Oh, Gaël's up. That's right.
All right. So how's everything going? Fine? Good. So we can get into the core of machine learning. All right. So in this section, I'd like to introduce you a bit to the basic principles of machine learning. So we're going to go over a bit the terminology and the kind of problems, so just so that you know what supervised learning and unsupervised learning is. We're going to give some basic examples of these problems with the Scikit-Learn. And we're going to go over the basic Scikit-Learn syntax and API. All right. So let me get a bit more space while they'll do it. Okay. So I mean, machine learning is a fairly, if you look at the machine learning literature, it's a fairly formal literature. And one of the problems is turning your real life problem into this formal problem. So to think about the formal problem, the idea is that you want to build a program or a decision rule to make decisions from data. And this decision rule will have a set of tunable parameters that you're going to learn from data. So you can have a decision rule without tunable parameters, but then it's not machine learning. And so as we've seen before, we're going to mostly, in all these examples, be working with data that is in a 2D representation, which is number of samples times number of features. I think we've covered this. And so as the previous questions showed, there might be a challenge to go from your real-life data to this representation. It's quite often a very important step. We call it feature engineering, feature extraction. To be honest, it can be much more important than the machine learning step. But that's mostly domain knowledge. It's not something that we can do for you. So you've got to think about your data. If you got images, you may need to rescale them so that they have the same shape. You probably need to adjust the contrast. You may need to extract edges. And that completely depends on your problem setting. And one thing that we don't want to do is to discuss this too much, because we think you come from different domains of science and engineering, and you have different kinds of data sets. All right, so we're pretending that this problem is solved. And we're moving on to the next problem, is that you've got a set of good features that, oh well. That's fine, I don't need the screen. I have it. Right. I don't know, I don't think I did anything. I think the system rebooted. Apple computers don't like me.
Can these algorithms handle missing data? You know, if you have a big old array of
Okay, so the question was, can these algorithms handle missing data? And the answer is no. So missing data is a big and an important problem. And in most algorithms, we've decided not to tackle it because it just, I mean, handling missing data in all the algorithms would be a tremendous amount of work. So I know at least of one algorithm in Scikit-Learn that handles missing data. But in general, we would advise you to either, if you really know what you're doing, just grab the code and add to it in your copy a strategy for missing data. Did you catch the AV guy? Yeah. Okay. Cool. So we can go on talking. Or a more generic solution would be to have a generic data imputation strategy, which is what's often done. So basically, you've got a first pre-processing step that imputes the missing data. And one very common strategy would be, okay, so I've got a bunch of features and a bunch of samples, and in some samples, some features are missing. So if you know the class of the sample, you might assign to the missing feature the median of the feature across the other samples of the same class, and if you don't know the class, it's going to be the median of the features across all the other classes. That's a very simple way of going forward with it. In general, if you know your data, you probably have a better way of doing missing data imputation. And we have a Google Summer of Code student who's going to be working on things that go in this direction, which are recommendation systems, and that we hope to use for generic feature imputation. Any other questions?
What's the name of the algorithm? Can you describe the algorithm a little bit?
For
It was linear regression, but I mean, it's multivariate linear regression. What is the generic name for that?
for
What you're going to describe in your lecture?
Oh, in there. So yeah, my first example is going to be a linear regression example. I mean, it's an ordinary least square regression. So the algorithm, I mean, is a closed form formula for computing the coefficients. So the algorithm, I mean, is, I don't know of a name, but I mean, a good exercise is you can look it up. I mean, you can look up, so you take the linear, so I can just describe orally what's going to happen on the notebook. You have the notebook, so we're importing from Scikit-Learn, we're importing, so from Scikit-Learn linear model, we're importing linear regression. And so now you have your linear regression object. And so one of the questions was, okay, what's the algorithm? Well, you can try it. Hey, cool. Nope. Oh, is it the laptop that's not working?
Yeah.
Okay.
It is max.
I could have used mine. All right, thanks. All right, so there we are. That's the right. Cool, now I get scrolling that I understand. Yay. All right. So we were saying, okay, so we're importing, right, so we're just going to rerun these basic imports. Oops. And we were saying, okay, so yeah, we're taking a simple example of a learning task, which is the linear regression. And you can immediately see that, so linear regression is also standard statistics. So machine learning statistics, they're, I mean, both views on the same problem, which is learning or inferring or estimating data, parameters from data. And so here, just as an example, as a very simple example, we are importing the linear regression object from Scikit-Learn. And there was a question on what, ooh, fancy, different icons. A question on what the algorithm was, and one thing that you can do is to have a look at the fit method, and you can do 2 question marks to see the code, And if you're lucky, the code will tell you. And if you're not, well, right. And so what you can see here is that the algorithm is used in there, and it's this least square object. And then you have to dig in to see where it comes from. And so what we're seeing here is that in some sense it's very simple, and in other sense it's not, because we're using a different code, whether for sparse and non-sparse, for multiple output or not. But the core idea is here we're using a lineal least square, which you might know, standard SciPy. And the value comes from the wrapping of this lineal least square into something that will support the different data types. All right. So in general, I would encourage you, when you've got questions, you don't know what the code is, to look at the code. We hope that it's somewhat readable. All right, so how you might use this linear regression object? Well, you want to instantiate it and give parameters to it. We've seen examples of instantiating estimator objects previously with the dict transform object. So we're instantiating it and telling it that we want to normalize the data, and then we're just looking at the model.normalize attribute, which is to true, right? So if I had said normalize equals false, then we'd have model.normalize false. And we can look at our model object. And it's a linear regression, and it has a set of parameters as copy X, fit intercept, or normalize.
What is copy X?
All right. So what is copy X? Well, the way you figure this out is you look at the documentation of the linear regression object, and you can use a question mark for this on. And then here you've got, oh, and it's not in there. I think I noted that when I was writing the tutorial. Okay, so what is copy X? So it's not in documentation. We should fix this. But so you're giving X. In Scikit-Learn, we call X the data matrix, so the data, and Y the target. So you're giving X to the algorithm, and you want to normalize the data. So you can normalize in place. You can remove the mean and divide by the variance in place. This is great because you're saving memory. This is bad because if you're keeping X and you want to use it for something else, well, you're going to have surprises. So by default, we don't modify the data in place. And you've got arguments like copy X, copy Y, copy something to many of the algorithms that will change this behavior if you set them to false. They will not copy the input argument, and they will modify it in place. So if you know what you're doing, it may be interesting. By default, they're set to false. By default, we always choose the safe settings, even if they lead to a performance cost. Okay, yeah, so this is a good example of a very simple learner, simple estimator, of the fact that it's got parameters that they should be described in the doc string. We try to have parameters somewhat homogeneous in the Scikit-Learn, so if copy X will mean the same thing everywhere. All right, so we have data. So I'm going to create the simplest data ever, which is 1, 2, 3 as features. Well, no, 0, 1, 2 because I'm Python. And 0, 1, 2 as target. And then I'm going to plot them. Okay, so I'm trying to learn Y from X. That's the problem. I need X to be a 2D sample by features matrix for Scikit-Learn. So I'm going to expand it being 2D, right? And then I can fit. So model.fit will learn the model parameters from X and Y. So you can see there's a convention in Scikit-Learn which is capital letters. So single variable name capital letters are matrices, and non-capitalized letters are vectors. Okay? And so I fit from the data, and once I fit from the data, I have learned model parameters. In Scikit-Learn, model parameters are attributes of the object with an underscore at the end. If you do statistics, variables that are learned from data, they have a hat quite often in the papers. So we don't know how to do hats in Python, so we just do an underscore. And so we've learned one coefficient because there was only one feature, and this coefficient is 1. So basically, x equals y. All right? So that's a simple example of a very, very simple learning strategy. And we'll come back to it. So, as we've mentioned before, there are two classes of problem. Classification, I'm trying to learn different classes, so different classes of irises. Regression, I'm trying to learn a continuous setting, continuous variable. So there are different, here we're giving different examples of this task. I mean, you could be, this is the kind of thing that Jake does. You could be using images that come from astronomy. You could be trying to recognize people from their pictures. You could be looking at what's known as the Netflix problem, which is trying to, knowing what movies somebody liked, trying to suggest new movies that this person liked. This is a fairly specific learning problem that we're not going to cover here, the Netflix problem. So I'm going to give a simple example of classification using our favorite classification data set, which is the iris one. So I'm going to load the iris data set. We've done this before. So you setting x and y to the data in the target. And then I'm going to use a simple estimator for classification, which is the k-nearest neighbor estimator. So the k-nearest neighbor estimator is a very simple rule. Basically, you have a bunch of labeled data. Given non-labeled data, you're going to look at the closest labeled data to this unlabeled data and say, well, it's probably in the same class. Okay? So closest is in the sense of the features that you're giving it. And so that's the one nearest neighbor. But you can have another decision rule, which is to say, well, I'm going to look at the k closest and then have a voting heuristic on this. All right? So if we create the one nearest neighbor and we fit it. All right, so we fit it on the data. And then we use the predict method to predict new data. So my question is, what is an iris that has 3 times 5 centimeters sepal and 4 times 2 centimeters petal? I don't know the answer, but maybe my algorithm knows it. And my algorithm tells me it's a Virginica. Okay? So the important things are the fit method, the predict method that takes x without y, so 2D matrix of samples by feature, and returns y, 1D matrix of labels. And I've just transformed this label, which was an integer, into a name using the target name list. Okay?
About your n neighbors, so if the number of clusters here is assuming there's one cluster, or because the number k, right? So k means k clusters, so where is the number k?
All right, so the question is, where is the number k in this in this code? So the number k is actually n neighbors, right? Even though it's called the k nearest neighbor, we've decided to use n neighbors as a parameter because it's more explicit. And when you're reading code, it's easier to know what this parameter is rather than k. It used to be k, and we changed it. Does that answer the question? Okay. All right, so here we can look at the prediction. Yeah. Okay. All right, so here we're looking at the prediction. So we're looking at sepal width and length, and our samples are displayed as scatter plots, as previously. And the prediction of the k-nearest neighbor is displayed as the color of this, this region of the feature space. Okay?
My eye and a lot of most people have a warning here.
Yeah,
So what's the warning?
depends on data order.
Yeah, I got that.
Okay. So that's interesting. Why don't I have that? Probably because these warnings are displayed only once. Okay, so... Oh, yeah, correct. Yeah, correct. So the reason, so that warning is no longer in master. That's why we don't have it. But the reason is that I can't see it here, but you probably have two data points that are exactly at the same position. Yeah. And they might have different classes. So now in terms of k-nearest neighbor, this is, when you're trying to find the k-nearest neighbor, if these two data points sit right at the border of the distance, it's which one are you going to pick? You're going to pick the first one. So that depends on data order. Does that make sense?
Our data is different from yours.
No, my code is different from yours.
Why'd you take the warning out?
Jake?
We took the warning out because it's annoying and it pops up too often to be useful. So we found that people were basically just filtering it out because it popped up all the time. Because essentially, anytime you have integer features, you're very likely. Anytime you have integer features, you're very likely to have 2 points that have the exact same distance away from each other. So that warning pops up in lots of situations, and it became more annoying than helpful. So we, instead of having a warning, we moved it to the documentation.
That said, I mean, you can see on this data, this data are people that went around and measured length and width of sepal. And you can see that they've rounded what they measured. You can see it on the plot. I mean, the dots are on a grid, so clearly they've rounded things. So in general, don't do this. Okay, you've got noise in your data, but machine learning is about learning from noisy data. So just put the noise in. Don't in general, that's a general advice. It sometimes will not be the best advice, but in general, don't, unless you really know what you're doing, round up things. All right, an exercise. Can you, so you don't know much about Scikit-Learn so far, but can you try to learn on the same problem to use the SVC classifier, which means support vector classifier, which you will find in scikit-learn.svm.svc. And you try to use it as a black box. And if you finish early, so if you can quickly predict what the class of the 3542 feature is, sample is, then you can try to do the same plot than we did above. So are there other people that have interesting errors trying to use the SVC that tells them that it doesn't have an underscore sparse attribute? What's the, can you check the version? So did everybody get a prediction? I'll try to get one too. You got a different answer? Oh my word. The machine is not always right. Not here. You got a different answer. Versicolor. Well, I say version, okay. So what you did different than I did? All right, but anyhow, I mean, you could get a different answer. There are different problems. One is that there's noise in your data, and it's not clear how to draw conclusions. And the other one is that the algorithm is not perfect.
You could have, I put 1.0 in there for the default, but I guess you could put something different, and then you get a different number, right?
For what? For
So
the
if I, let me try.
for the C parameter.
Yeah, if I go 0.5.
Yeah. We'll cover that afterwards, yeah, how you set parameters. Okay, so what comes up here is that there are parameters in the SVC, and if you change them, you might get different answers. And of course, this is a problem, and we'll cover this later. But yeah, this is a core problem.
Is there a way to get back the confidence that the predictor has with it?
All right, so the question was, is there a way to get back the confidence? For certain predictors, there is some way to get it. And the good news is, I believe the SVC can do this. One thing is you're just going to have to, so I'm going to insert a new cell. And you're just going to have to tell the SVC that you want probabilities. So we call this probabilities. And if you look at the documentation, the docstring, it's got a probability keyword. So we're going to set it to true. And then we're going to fit. And what we're going to do then is that we're going to call the predict proba, so predict probability of the object. And it's going to give us, well, I'm going to run this and we'll see what it will give us. All right, so we call predict proba. So we fit the SVC with probability equals true. The reason we have this parameter is that computing probabilities is an additional cost to it. In this specific case, it may, for the SVC, it may not always be true. And then we're calling the predict proba. And it gives us a vector of probabilities for each class. So it should sum to 1. Let's check. And so the most probable class is the one with the highest probability. Does sum to 1. Okay, now probability estimates are, of course, depending on a model and an algorithm to infer it. They're never going to be perfectly true. So what this does here is that it bootstraps the data and then fits a probabilistic model to it. Okay, and it's going to depend on the estimator that you use. Some estimators, most estimators, I believe, will not have a predict proba. and the way that the probability is inferred is going to depend on the estimator. All right, so and I will not cover the plot in the interest of time. All right, we're going to go through a regression example. So we're going to go through a linear regression. We've already been through this, but we're going to go over it again. So we're going to generate some simple data using just a random number generator. So first I'm going to seed it. I've grown to really trust seeding random number generators, because if you don't, then you're not going to reproduce your results. And we have, in Scikit-Learn, there are many places where random numbers are needed in Scikit-Learn. And each time you get a random state parameter to the object. That random state parameter may be a seed or a random number generator or none. If it's none, it's going to use the global random number generator. If it's a seed, it's going to use its own random number generator that it seeds. It's not going to modify the global random number generator. And if it's a random number generator, it's going to use it. Okay? That's a technical comment, but if you get more into this, it might come in useful. So we're generating next matrix with 20 samples in one feature. We're generating a Y matrix that is just a linear, an affine transform of X, and adding some noise to it, and that's the important thing. We're adding normal noise to it. We're importing our linear regression object. We're fitting it using fit intercept equals true. Okay, what does fit intercept do? It tells you that it's the model accepts having an offset, which is known often in the machine learning literature as an intercept. So for linear models, they can have an intercept, and in which case you want to put fit intercept it equals true. And so we fit it, and then we can look at the parameters that have been estimated from the data, so coefficients and offsets. And then we can plot both the predictions of our learned model on a grid of points, a lin space, and the actual true model on this grid of points. So this is what we called X-test, so where we want to test our model. We're using lin space, and once again, we're adding an extra dimension because the data should be samples by features. And then we're using the predict method of the model that will now return not a class label, but a continuous quantity. And we can plot this. So if we run this code, this is what we get. Blue is our training data. Green is our predicted data. Does that make sense for everybody? So this is the core API of Scikit-Learn. If you know this, you can use it.
Can you take into account if you know that you point at errors?
No. We are not taking into account errors. Was it?
Just like missing data.
Yeah, I mean, just like missing data, some algorithms could. Typically, linear regression, you could do something like a weighted linear regression. Quite often, this is more seen as something in the ballpark of statistics, but there is, of course, a continuity. Quite often, the paradigm in machine learning is, well, if you know your data has error, it's probably that you extracted it from something else. Give me what you extracted it from. All right, I'm going to cover a bit on supervised learning. So unsupervised learning is a different sort of problems. It's when your data has no labels. So I've got X and no Y. And then in such situation, you're interested in exploring and inferring the structure of the data. And so this is a very wide set of problems. And you can have tasks such as dimensionality reduction. We're going to cover a bit more of these things in detail. So clustering is, well, suppose that we had measured this iris data set and lost the labels. Now we know that there are three classes, and from the data we want to try to find what the three classes are, what clusters together. and we're going to cover this later. You could be trying to separate out different signals. So suppose you're at a party, many people are talking together, and you're trying to listen to one specific person. That's a source separation problem. So it's an unsupervised problem. And so I'm just going to cover a simple example, which is to use PCA, principal component analysis, and we're going to use it here for visualization. And so if you consider the iris data set, one problem that we have with the iris data set is that we can't really visualize it. It's basically 4 dimensions. It's a block of data in 4 dimensions, and it's harder to visualize. So what we can do is reduce it to 2 dimensions. That's basically what we've been doing all the time. And the question is, how do you choose these 2 dimensions? And one way to do it is to say, well, I'm going to find the 2 dimensions that explain the most variance. Okay, so if my data does not have the same variance in all directions, it might have more variance in specific direction, and PCA will find this. And so once again, I'm going to create X and Y that are my iris data sets, except I'm not going to be using Y for the learning. I'm going to import the PCA object from the decomposition module in Scikit-Learn. So the decomposition module contains a set of different decomposition algorithms. So PCA stands for principal component analysis. So ICA is independent component analysis. These are all decomposition algorithms. PCA takes a parameter that's the number of components that you want to fit. Because we want to display it in 2D, we're going to take 2 components. Once it's instantiated, all I have to do is to fit it to the data. Then PCA gives me a new method, which I haven't used so far, which is a transform method that I can apply to data. And that will give me a reduced data set. And then I can plot this reduced data set. And this reduced data set is now n samples by 2 features data set, because I've asked for 2 components. And so I can now plot it in 2D without any problem. And I can run this. All right, so my reduced data set is 150 by 2. This is the plotting. And what I've done also is, so PCA has learned components that have 1 floating point value per original feature, right? They're vectors in the original feature space. So what I've done here is that I've printed these in terms of the original features. So what you can see is that the first component is 0.362 times the sepal length, blah, 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 right? So this is the meaning. So in a sense, it's hard to interpret it in the original features. My first component is not directly linked. Well, it is directly linked to my sepal length, but it's a mixture of many, many things. Because these are the directions that capture most of the variance of the data set, they can be very useful for learning or for visualization. And so what you can see is that, can we see this? Yeah, somewhat. I mean, I would expect, one thing that I would expect is the whole thing to covary. I mean, basically, if I've got bigger, longer sepal, I probably also have longer petal and wider sepal and petal. And this is only partly true here.
So here you're dictating the number of dimensions you want, right?
Uh-huh.
And components of
Mm-hmm.
those 2. What if you didn't know how many dimensions it would be, and you just want to get the most total variance? Would there be a way where it would go and find out, like a street plot or something? Oh, well, you need 3 or 5 or whatever.
All right, so one thing that we don't do in Scikit-Learn that packages like R might do is plot things and ask you for your feedback on deciding, because our focus is really to write things that run without human intervention. That said, you have a good point. There might be ways of deciding how many components we want. And I can't remember what we have in there. I know we have some, so normal PCA can do it.
Yeah. So just let me put the constructor power.
None. Okay, so if you do none, yeah, well, that's not what it's looking for. If you do none, then it uses a maximum likelihood under a certain model. But typically, I mean, one thing that would be really useful is to. Yeah, I mean, but that requires human intervention. I mean, what you could do is. And I'm putting no number of components, and then I'm fitting it to the data. All right, and then we can have a look at.
Oh, I see. And it's going to get you the optimal.
Well, optimal under a model. All right, so one thing here is that to compute the optimal under this certain model, I had first to compute all the decomposition. So here there are only 4 because we've got 4 features. And you can see here the explained variance. So the first feature explains just about all the variance. And then it slowly goes down. So if you want the ratio, this is how you do it. And so the number of components equals none uses a model to find, okay, what's the latent dimension of my data. Something that would be useful, and I don't believe we have, is to say, well, I'd like to keep at least 90% of my variance, which would be a good rule. And I don't think we have this. We should. All right. All right, that's fantastic. Cool. Equals 0.9. Okay, and then, right. Cool. Excellent.
But it does the full decomposition anyway.
Yeah, yeah.
So if you put it, if it's a double in there instead of the.
But yeah, I mean, one important remark is that if you specify the number of components, then it will not do the full decomposition, so it's going to be more efficient for computing power. And yeah, so there are different ways of setting it.
Does it depend on the data sequence and data order now?
No, it doesn't. That was a specific case for the k-nearest neighbor. Oh, sorry, I forgot to repeat the question. The question was, does it depend on the data order? And the answer was no.
Will the PCA do sparse decomposition?
Well, the PCA do sparse decomposition, I believe so. We can check. No, we need the randomized PCA, right?
Test, okay. So the regular PCA, as it is right now, I don't think it supports sparse input, but we could add the RPAC version, I don't know. And there is a randomized PCA, which is an approximate method that is able to do any kind of, that supports any kind of input.
Can I just point out that if you say the number of components is 2, then the program will bring back the 2 largest components.
Yeah, of course, yeah. It's always the largest component. So the question was, okay, if you ask for 2 components, am I getting the 2 largest components? The answer is yes, you're getting the largest component.
So when I look at this example here, and I see the plot, what's going on in the first line of code is that you set y equal to the target, right? And that's the information that the scientist has gone out in the field and collected and said, this flower is this particular species, right? So when you plot it, y is setting the color of the target. Now, if we were doing this without knowing, this is an unsupervised problem, right? If we were doing this, in real life, we wouldn't have any kind of target to plot with, right? So we would just see one kind of group on the left, which looks like it's clustered out there. But then, what do we do about that right column? Because they would all be gray dots. We wouldn't.
Okay, so the question is, okay, what if I was looking at, what if I were looking at this without the targets? So if I'm really in an unsupervised setting, we've really lost the targets. Worst case, we don't even know how many classes there are.
Yeah.
I'm looking at this data, and well, chances are I will not be able to say that there are 3 classes. Right, I mean, if you look at this, forget the color, give me this, ask me how many classes there are, I will tell you 2, not 3. Yeah, I mean, this is a very good question. Basically, there is a limit to what unsupervised learning can tell you. It's very hard. These are very hard problems in general, unsupervised learning problems. Unless you want to use it for a specific purpose, which we were doing here, which is basically some kind of compression. I want to go from 4 to 2. That's a reasonably easy problem because it's well posed. And I'm not trying to find to draw conclusions on a hidden structure. I'm just going to try to use it, and we'll see afterwards how we can use it. Now, if you're going to try to find hidden structure and draw conclusion on this, it's a very, very, very hard problem. And I'll go over this later. But I mean, I see people publishing papers on how many clusters they have in their data. Honestly, I don't trust these papers. I trust the results because usually the people come from neuroscience or biology and they know what they need to find, but they didn't need acquired data to find that.
Just for this specific problem, if you take the original data in 4-dimensional space, it's quite well separated. You cannot see it on this projection here, but the original data is well separated. So you could use k-means with various values of k, and there are heuristics, ways to find the optimal values of k. And it actually works on this one, on IRIS dataset. There are 2 different heuristics that get the same, but they are not implemented in Scikit-Learn yet. So
yeah, I disagree. I disagree. And I think k-means doesn't work on the data set, and I think we're going to cover it. But it's a question of chance whether it's going to work or not on your data.
I mean, I guess whether it's true or not, it's well separated in 4 dimensions, and shouldn't the PCA, isn't that the whole point of the PCA is to find the variable that separates them?
No, PCA is an unsupervised. That's a really good discussion that we're having here. So the question is, okay, if it's well separated in 4 dimensions, isn't the whole point of PCA to keep this separation? Well, 2 things. First, data that may well be separated in 4 dimensions may not be well separated in 2 dimensions. I mean, we can go from 2 to 1. Okay, so I've got this data set that's like this, and I've got 4 classes. All right. Now, this is well separated in 2D, not in 1D. So basically, my learning problem in 1D becomes impossible. In 2D, it is possible. And PCA will probably find this axis and then this axis. So it's PCA will, if I take only one component, will collide these 2 guys. Now, the second thing is, and that's a really important remark, is that PCA is unsupervised. It knows nothing about your labels. So now if I have this setting, and I do a data reduction by PCA, well, it's going to project along this direction. And so bang, I've got classes that are very well separated in my original space. They're not well separated in the PCA. I'm really happy that we're having this discussion because we're getting at the point that in general, of course, using an unsupervised method on a supervised problem is shooting yourself in the foot. Now, there might be good reasons to do this. One is that you might be able to have super fast unsupervised method that allow you to do a good data reduction. And if you get a good performance after this, it's probably that you're not in this situation. So I wouldn't in general say that you should never use it, but think about using supervised before unsupervised if you have class labels. I think this is a good time to break. Now, before breaking, I'll just run on the reduced data set the k-means algorithm. So k-means finds clusters So we're just importing from clusters the k-means object, telling it we want 3 clusters, and running it on the reduced data set and plotting the class labels that were found. Okay? I made the error of talking about break just before this example, so I feel that nobody's focused anymore. Right, refocus. So k-means is the simplest clustering algorithm. So what it does is it tries to group observations together. And here we're running it on the iris data set, and we're telling it there are 3 clusters. Now, telling it that there's 3 clusters is already telling it a lot, because looking at this data, most people would conclude that there are 2 clusters, okay? And then we're running it. One thing that's important is that k-means depends on a random initialization, and it will give different results depending on the random initialization. So we're setting the random state of this object just to be able to reproduce, okay? That's the random state parameter here. We're fitting, and then we're using the predict method of k-means. I'll be with you in a second. The predict method of k-means to predict class labels. And then we're plotting them, and we see that they don't match. And I'll just answer this gentleman's question.
Can you provide the starting positions?
Can we provide the starting positions? Yes, we can. There are a bunch of different initialization heuristics in k-means that you can control if you look at the docstring. That may be important. So about the big debate whether we're going to recover or not the ground truth using k-means, it might be true in specific cases, and it will not be true in general. And one thing that we could do would be to plot this on the full data rather than on the reduced data. And then see if we're getting close to recovered. Right, so the point here being that I'm giving it reduced data, so I'm making the problem harder for k-means. And actually, maybe not. But I could be making the problem harder for k-means. So what if we give it the full data? Oops. And I'm going to create a new figure and plot the ground truth. Okay, so one thing that's important to keep in mind is that clustering has, there's a permutation that you can't control right. You can see here that the colors don't match across between the ground truth and the predicted, the model that was learned from the data. But apart from this, you can see that there's a pretty good match. It's just a pretty good match. There's nothing that tells you that it will be a perfect match. With this, I think we should break. Yeah, break 15 minutes. We'll be back at 25 past.